So some of y'all may be wondering about, what's his fashion theme about today? Well, remember, this is Boy Scout merit badge, all kinds of them. You got 2 sons are Eagle Scouts. And look what we've been doing today with power systems all over the map, all kinds of stuff. Same kind of thing. You really want to have merit badges in a whole bunch of skills, well, for all of design, but particularly for looking at motors and actuators. And as we started to before, show you in terms of the umbilicals or the wire leads, very important topic. And you have already had some experience with batteries. And how do we get the energy stored and supply it to the actuator? That's what we want to talk about now. And then how do we budget for that? How do we calculate what the whole system is needing? So let's dive into batteries. If you ever happen to get to Lake Como in Italy, wonderful place, very nice, very beautiful, blah, blah, blah. And there's a very nice memorial to Mr. Volta, who invented the battery. Batteries are used all over the place, from your cell phone to the drill. More and more cars use batteries. It's absolutely critical technology for the planet. And you're probably not going to be designing batteries in this class, but you may end up being, even as a mechanical design person, designing battery systems with the chemical engineers and how they're packaged so they won't burn up. A key thing as a design person you want to understand is what are the different types of batteries, what kind of voltage can you get out, what kind of power can you get out, that means how fast can you get the energy out of the battery, and what's the total amount of energy that is stored in the battery. If it's a rechargeable battery, you also need to understand how it recharges, because that'll affect how the control system for your machine works if the battery happens to live with the machine. You also get what is called the energy density, or how much energy you can store in what size space, and that'll have a big effect on what battery you choose also. Because, for example, for a lithium-ion battery for portable drills, or all kinds of portable power tools, before lithium-ion batteries were around, you're not really going to use a lead-acid battery. That'd be way too heavy. Okay? So a lead-acid battery won't necessarily give me any more performance out than this thing will for this drill. It'll last a lot longer, but this is a lot lighter, and I can get the energy out very, very fast. That's called, related to what's called the C rate, by the way. So batteries, many different types. Start building your personal database of what each type can do, cost, how much energy, and what size package. Springs. Batteries give you energy which you can have with a controlled output based on the control. You can get all kinds of different springs where in general the spring is going to store energy and then release it suddenly, or give you a power assist over a period of time. So here, for example, is one extreme of a spring, very soft and floppy. And you can actually cut this thing to length. You can buy a long spring, and it'll have a spring constant over its length. And if I need a shorter one, I just cut it and get what I want. Yes, you too can get the spring constant you want. They're very easy to design with. And indeed, you go online to spring companies, and they got some very nice design tools. And you can design the spring you want, and if it doesn't exist in the catalog, amazingly cheap to have a few thousand springs made up, a few tens of cents a piece for a small spring. There are bigger springs, and I'm not going to crush this because I may break it, and I don't want that to happen. But for example, this is from an old car. And notice this kind of spring also bends sideways. And you may have seen these things in playgrounds where you put a chair on top of it, and then you get one of these bouncy, bouncy, bouncy chin type things. So a spring does not only have to be to store energy, it can also be kind of an entertainment device too. I keep this around just in case I need it. torsion springs, constant force springs. Normally a spring, the force is proportional to the distance you move it, but this coil of wire can give you constant force. Small microsilicon springs we've designed for electrical contacts, cantilever or leaf springs in your car. Very simple to design with. Very important as a spring not only to store energy, but to soften the load of things. Think on how your car, what it would be like if there were no spring suspension. If anybody's driven a tractor where the axle is fixed to the frame and you're speeding across a bumpy field, yes, you've got rubber tires and maybe a little bit of springiness in the seat, but in general, driving a piece of construction equipment without a nice soft seat, very, very painful. So springs and suspensions are very, very important elements. How much energy you can store in the spring and what you can get out of that, very straightforward calculation. For a linear spring, where if I plot force versus distance, F equals kx, amount of energy is stored, the area under this curve, so the energy equals 1/2 kx squared. Okay, F equals kx, so this is this point, times x, it's a triangle, 1/2 kx squared. So for any spring, you can calculate the amount of energy you get out of it, and thus determine if you were to suddenly release it, how much energy you get back out. Similar relationship for a torsional spring. You use springs often for storing up the energy and then with a trigger, releasing it for like launching a projectile for a design contest, designing a stapler. Automotive suspension, you want to take the load, but then you want to get that force to raise the car back up. Unbelievable amount of applications for springs. Let's talk about a different kind of spring, and also an actuator, a pneumatic spring. And think of the tailgate in the back of your car. And I just happen to have such a spring here. It's called a gas spring. Let's try not to hurt ourselves. Very stiff. Wow. Why is it so stiff? Remember, in the tailgate of your car, it's attached. The tailgate hinges here. The spring is attached here, and you have this long, big, heavy gate out here, which will then close this up. So this is a gas spring. Here I have a pneumatic cylinder, and this is what's called a double rod cylinder. So in the middle is the actual piston, and it goes back either way. And watch what happens if I close up the output. See, well, I'm not fully sealing it. Let's try better. See, that's a spring. I'm compressing it. And so you can use a cylinder as a gas spring. You ask the question, why was this one so stiff in such a smaller space? What did they do in here to make a gas spring so much stiffer? Is it pre-pressurized? Might be some interesting patents in this thing. Look and see how they did it. Whoever invented that obviously had a great idea, because they're used all over the place now. You wouldn't want to have a big spring like this, something that's too big in the back. It's got to be small. So pneumatic systems can act as springs. They can also act as actuators. So for example, if I connect up this piston, and I suddenly apply a lot of pressure to it, it'll go out very quick. So one of the reasons why pneumatic systems are nice is I can have pressure stored up, release it with a valve, and they can move very, very fast, very low cost in a very small space. To have an electronic actuator move with this long range of motion in this kind of a very lightweight package would be very, very expensive, for example. So pneumatic systems are not necessarily Oh, that's so old, that's so 20th century, dude. So for example, watch what happens here. Nothing. Why did it start moving once I gave it a little bit of hit? Why wasn't I able to get it moving just by blowing into it? Watch this. Into moving. And then watch now. I'll give it a little bit of a kick. And I'll stop giving it a kick and I'll keep going. Why is that? What's happening? Why wasn't it this pure linear system? The key is looking inside the cylinder, and this is a very important part when you consider a pneumatic or a hydraulic system. Here is the cylinder. The outside part, by the way, is called the cylinder, or the barrel. What's actually called the piston is this thing in the middle, this little round thing in the middle here. This is the rod. On the end of the rod, you'll often have a part with a hole in it, threaded onto it. But if you have something that looks like this is called a clevis. This is the cylinder, rod, piston. And if it's a single acting piston, it has a port here. The double acting piston, you're going to have, this is here called the rod gland, or the front seal to the piston. And then here is the other port. Such that when air flows in here, it moves this way, whoop, and air has to flow out that way. So what was causing this, when I put this little bit of pressure in, not to move right away? And you see, the reasons I blew in it to make it move was if I just connected up to my air compressor and hit, it would go funk. I want to demonstrate this initial nonlinear portion of motion. Well, in here you've got a seal, and there's a certain amount of friction. And later on in our segments on bearings, you'll understand that friction, there are two types of friction. There's static and dynamic. And if I were to plot velocity versus friction, at no velocity the friction's high, and the minute you start moving, the friction drops precipitously and gets lower. The reason this is important in pneumatic systems is if you're trying to get very precise motion or very precise force, you have to recognize that there is some initial stiction that happens. Most systems it doesn't really matter about, but it's something you need to be aware of, particularly for hydraulics machines where the pistons may have to be very, very tight in order to accommodate or hold back very, very high pressures. Okay? You can use pistons in all kinds of machines. You can control the flow of fluid, liquid fluid through a piston in a hydraulic system very, very accurately using something called a servo valve. In a pneumatic system, it's a lot harder to get good control of velocity. You can do okay, but the challenge is the compressibility of air, whereas when you're in a liquid system, it's basically not compressible for most intents and purposes. Okay, very, very useful, and if you didn't have hydraulic cylinders, we wouldn't have the planet that we have now, because that's what all construction machinery is based on. Now, pneumatic systems, as we showed earlier, can act as springs, which means they can store energy. Pneumatic systems can also store energy if you have a big compressed cylinder. So for example, let me get my bottle assistant. If you take a bottle, and please don't actually ever use soda bottles as a compressed air storage. So I've got a lot of energy stored up in here. And when you get enough of it, if you were to suddenly pierce it, it would escape. If I had, let's say, 10 atmospheres of pressure in here and it was punctured, poof, it can come out. And depending on the material, it may just tear, this is called leak before break, and not hurt anybody. If you were foolish enough to use something that could shatter, then it would go off like a bomb. This is where some people really get in trouble. And believe me, I know about things that go boom when they use plastic like PVC as in potato cannons and things like that. Or they'll pressurize a PVC cylinder to store pneumatic energy. Do not ever do that. Never use any kind of hard plastic. You say, well, how do I know? Well, take what you intend to using it and whack it with a hammer and see what happens. Whack it with a hammer when it's cold and watch what happens. If you're going to ever store energy in terms of pressurized gas, you really want to use, they're called accumulators, real pneumatic elements made of steel or aluminum, designed well so they won't explode. Okay? So you've got to be very, very careful when you store energy as a pressurized gas. Where do I see these pneumatic energy systems? Remember, a spring is an energy storage system. So like here, this is in a mountain bike for the gas shocks. Okay? And of course, there's some spreadsheets for calculating forces in pneumatic cylinders and the amount of energy you can store in a pneumatic vessel. Using pneumatic cylinders, hydraulic cylinders, excavators, robots, very common in automation because in a very small space you can get very repeatable linear motion. The most important thing is to make sure you're aware of the force, the inertia of the elements itself, and how that affects. Remember, force equals mass times inertia. And listen. That sound of the fluid going through the restriction in the hoses. Oh, yeah, like Ohm's law. Remember we talked about that? That flow around a corner, flow through a hole is a resistance. So that will limit how fast you can move things based on the ease of the flow of the fluid through the system. And you're all really good now at designing linkages and understanding about, remember, Grashoff's criteria for the mobility of a linkage. Do you have the degrees of freedom you want? Look at all this beautiful 6 degree of freedom linkage here. Now, be it batteries, springs, pneumatic pressure vessels, whatever you do in your machine typically will have a lot of things it's doing, and it's got to keep doing it for a long time. And every time it makes a move, it consumes energy. Tying this back to where we very first started with how much power does it take to move. Remember that? If you want to cut the time to move in half, it takes 8 times the power. When you're designing your machine and you have a bunch of different actuators and a bunch of different moves in your machine, you want to start constructing what's called the power budget for the machine. What the power budget does is it lists all the different motions you want to do, the force anticipated in the motions, the velocity you want the force to occur at, and this is a very simple linear relationship here. This type of spreadsheet can actually include the force versus velocity profile. The total distance you want to move, the efficiency of the system. For example, is it a lead screw, or would be much higher efficiency for that motion if you had a ball screw running on ball bearings? Efficiency would go up. And for each one of these axes of motion, and as you build this engineering spreadsheet for your power budget, you start calculating the power to move, how much power is going to be dissipated in the battery, or whatever your energy system is. What is the net total energy required for the move. You need to do this for all the axes of motion and come up with, here is the total power my machine needs at any one point in time. Here is the total energy the energy storage system will have to provide over the range of motion for all the axes of motion. And make sure that you're storing enough energy on your machine to accomplish all the moves that you need to do in the time it has to between battery recharging. Make sure that the battery is able at any instant in time to get enough power out to serve all the axes of motion with the power they require, that's the energy per time at some unit in time, to move. Otherwise, you may say, okay, I can move this axis like this way, and this one like this way. Oh boy, that's really good. Now I'm going to turn my machine on where they're both supposed to move at once, and they go, so wait a second. One at a time goes this, this. But together they go like this when I want them to go like that. What happened? I couldn't get enough power out of the battery to give each axis what it wanted. I will play it again. Full like, yo! Okay, so a power budget working through systematically each axis at a time, which is just nothing more than a spreadsheet, is a really important part to close the loop on your systems engineering. The little case study you all should read by yourself and go through is this gear motor performance in terms of how we build a system to measure the performance of a gear motor that we wanted to use in this design class. How was it done where we hung weights off of it that it did or did not influence badly the performance of the motor itself? This is one of the reverse engineering pieces to study and look about it and think about. And as you go through things, what worked well, what didn't work well, try to spot the things in what other people report or you observe that, hey, yeah, I can see that fundamental principle working here. Wait a second. It doesn't look like they did it right there. They violated this fundamental principle. What happened? So in review, have you got enough power, like we just talked about? Have you got the proper transmission ratio? And of course, these two combined for your machine, have you got the battery, the motor, the machine moving the way you want it to move to give you total machine happiness?